we'll have the first webinar of 2026, and it is my pleasure to introduce our speaker. So Professor Michel Bellet, that is just in the room close to mine. He's one of my colleagues. So he's a professor in École des Mines de Paris, that is one of the major engineering schools in France, belonging to the now to Paris Sciences et Lettres University, and he's based in Cimet, south of France, and the center research is dedicated to material forming. So his research focused on thermomechanical molding and numerical simulation of industrial processes, mainly involving solidification. That means that it includes casting, welding, and today he will talk about additive manufacturing. So he has been highly involved in teaching and also in PhD student supervising. He's currently the head of the Department of Mechanics and Materials in Paris. And he has supervised up to 50 PhD students and co-authored more than 80 papers. In the last years, he has focused his activity in additive manufacturing, and he has supervised 10 PhD students and wrote more than 20 papers on the topic. So, the floor is yours, Michel, to talk about laser metal additive manufacturing, thermomechanical modeling, and numerical simulation at meso and macro scale. So what's the program?
Okay, thank you very much, Katia, and thank you, Sandrine, and all the ESAFORM staff for the invitation today to give this webinar. And thank you to all of you who will spend some time to listen to this point on additive manufacturing. So it's time to share my screen. Okay, share it. Okay, yeah. I hope you can see it plain screen. That's okay.
Yeah, perfect.
Yeah. All right. So on my side, it's okay also, and it's all right. So the point today is on the thermomechanical simulation of additive manufacturing, and more precisely, laser additive manufacturing. So I will acknowledge first contributions of different PhD students. You can see the name on this slide, and together with my colleagues in the staff, Charles-André Grandin, Gilda Guillemot, and Yanchen Tsang. So, the content of the webinar today, I will make a brief point on the main processes for laser additive manufacturing. Then we will insist on the main physical phenomena that are at work and that control the process, and how they can be modeled. And we give some example, and we will discuss numerical simulation, both at track scale and at part scale before concluding. So this slide presents the main additive manufacturing processes by laser. So laser is in charge of supplying energy, and the material is provided under the form of either powder or wire. So on the left of this slide, you can see the two major, let's say, laser powder additive manufacturing. On the very left, you can see LPBF, so which is the selective melting of successive layers of powder. You can see the laser at work on this animation on the left, melting and solidifying successively different layers to make finally a part. This is a process that has a low deposition rate, a few tenths of cubic centimeter per an hour. And beside this, you have another process which belongs to the directed energy family, DED processes, and in which powder is supplied coaxially with the laser beam, and the powder can be melted in flight or in the melt pool created by the laser, and then a track is formed. This is the powder DED manufacturing process that you can see on this animation from beam machines. Okay, so the deposition rate is a little bit significantly, I would say, higher, as you can see. And beside powder, you have a third major process for laser additive manufacturing, which is WLAM, like wire laser additive manufacturing. So here the material is supplied under the form of a wire, and this wire will be melted by a laser beam, and the laser beam can be divided in three or is transformed in an annular shape, and the laser will hit the wire and create concurrently the melt pool in which the wire is plunged, like this. So the wire contacts the substrate of the deposition previously deposited, and here the melt pool is much more extended, and so the deposition rate is quite high, an order of magnitude higher than the one you have in LPBF. So in this presentation, I will focus only on LPBF, which I found more consistent and more conform to the time allocated for this talk. Anyway, in the discussion session, if you have some questions on DED, laser, or wire laser additive manufacturing, I will be happy to answer and give you some examples as well. Okay, so why do we focus on thermomechanics? It is obviously to try to predict and to bring information regarding thermomechanical features and defects that characterize LPBF. I'll give you an example on this slide of some defects like porosities that you can have at the bottom of the let's say the melt pool after solidification, due to fluid mechanics. Other examples are some cracking that you can find in the vicinity of the melt pool, like shown here. And those cracks can be of two types. They can be cracks in solid state, like usually I would say, or more critically maybe what we call hot tearing or solidification cracking. That's crack that form before solidification is complete. In the last stages of solidification, where you have some dendrites growing in an epitaxial way from the previous deposition, and during this dendrite growth, when solidification is almost complete, some films, liquid films, can be fractured, provided that you apply a certain stress perpendicular to the growth direction, I would say. And this is a defect, since at that time the meshy zone is not permeable enough for the liquid to heal the crack, and so the crack remains. And it is very characteristic because the dendritic surface aspect can be seen along the crack surface. So you have also, I would say, more classical cracks that are simply due to thermomechanical effects, deformations, and combined stress. that may occur because of the uh, cyclic temperature that is undergone by the material due to the successive layer deposition. Examples are given here. So we can realize that the scale at which those phenomena will be studied can be very different. It will be very at a fine scale, at the melt pool scale, I would say, for solidification cracking or crack in the vicinity of the melt pool, but it can be at a more macroscopic scale to study cracks occurring during the construction of a part. Okay? And then that leads us to consider very differently track and part scale. And to let you realize a little bit more these different scales, I would like you to realize that in a 1 centimeter cubic of material, in LPBF, considering a classical layer thickness, 40 microns, for instance, and an interscan of 50 microns, which is quite classical, then in a single 1 cubic centimeter, we may have about several hundreds of meters of laser scans. So this is quite impressive, and obviously following the track, the laser scan path is not possible at the scale of a part. So very clearly we will distinguish the track scale, in which we will include the modeling of a precise modeling of the laser interaction physics, and at part scale we will be obliged to assume simplifying assumptions in order to predict the thermomechanical regime during construction of a part. Okay, so if we focus first on track scale, let's visit the main physical phenomena and their modeling. So laser matter interaction, I will talk about vaporization and surface tensions effects. So to begin with laser matter interaction, so what we learned from solid physics and photonics interactions between electrons and photons is that for metals, the absorption of a classical infrared radiation, that's the more convenient and the more frequent laser radiation that we have in additive manufacturing, then absorption will be made in surface within, let's say, maximum 20 nanometers. So there is no transparency of the material to this kind of radiation. So along the material surface, we will have absorption plus reflectivity equal 1, no transmission through the material. And what characterizes metals against infrared radiation is really a high reflectivity. This is a chart of the reflectivity, the reflectance of different metals considering the wavelength. And for this classical 1060 nanometer radiation, you can see that the reflectance is in the range for iron of 0.7, 0.8, so very high. So only a few part of the laser radiation will be absorbed by the material. So regarding the beams, laser beams, they can be Gaussian, hyper-Gaussian, or what we call top hat, or even shaped, and there is a lot of work going on now on sophisticating the energy distribution within a beam. So here you have a simple example of how the energy distribution may vary when you depart from the focal point of the laser beam. So it can be Gaussian, far from the focal point, or top hat near the focal point. And that's results from colleagues of École Normale Supérieure in Paris-Saclay. Okay, the main phenomena that governs the melt pool, one of the two mains, let's say, is definitely vaporization. So I will not enter into the detail of the equations governing vaporization that are inherited from all the studies on the laser physics, cutting with laser or piercing with lasers, and all this has been inherited and considered in laser additive manufacturing. So you have the saturation pressure and considering the Clausius-Clapeyron equation here, the temperature of the surface, and once the temperature of the surface exceeds the vaporization temperature at the atmospheric pressure, then this defines a saturation pressure, and this saturation pressure will conduct to the evaporation rate of the material in kilogram by second by a unit surface. And beta is a coefficient depending on the regime of evaporation, but in additive manufacturing, let's say beta is in the range of 1.17, 0.18. So two consequences. One small consequences, I would say, or moderate, is that evaporation will create a heat loss at the interface liquid gas. And the second consequence is that it will create what we call a recoil pressure. This is simply due to the conservation of momentum. You have evaporation, as you can see here on the right top, of a plume of metallic vapor from the melt pool, that is just here. And because of this very rapid evaporation, very rapid because of the drastic change of specific mass, and because of this rapid evaporation, you have a recoil pressure that will tend to deflect the pressure, the surface of the melt pool, and create what we call a keyhole when this deflection is very marked. And other consequence of this vaporization, because vaporization will create an ascending current of gas, let's say argon, which is the protective gas that is used in additive manufacturing classically. And you have this this ascending movement of argon. And because of that, you can have instabilities in the powder bed. For instance, particles that will be entrained in the flow of argon that can be melted when passing through the laser beam and being ejected on the part that is on the deposition that is in course. So that is a source of instabilities, of defects. Okay, but definitely one regarding the shape of the melt pool and the porosities aspect that we have seen, formation of the keyhole, that's the main effect of vaporization. And the second main driving force in the melt pool is surface tension, of course. Surface tension, maybe probably you know the effect of the surface tension acting as a force directed towards the normal of the surface. Here you have the surface tension, and here the curvature of the surface. So the curvature that can be the divergence of the normal to the surface. So this is one, I would say, stabilizing agent along the melt pool surface. But the main driving force is the action of surface tension tangentially to the surface. And that's what we call the Marangoni force. And this is due to the gradient, in fact, of the surface tension along the surface. And this gradient up to a first order is governed by the fact that surface tension is temperature dependent. So since you have a laser impacting the melt pool, then you have a thermal gradient along the surface of the melt pool. And then, because the surface tension is temperature dependent, you will have a gradient of surface tension. So you may consider two situations depending on the fact that the surface tension will increase or decrease with temperature. See, if surface tension increases with temperature, then because of the temperature gradient like this, then this will create surface flows towards the periphery of the belt pool. And conversely, if you have a surface tension that increases with temperature, surface tension will be maximum in the center, so this will create flows towards the maximum surface tension, and then because of conservation, flows going deeper in the material and creating a deep melt pool. Okay. So once these main phenomena have related equations, we can think about implementing this in a numerical simulation at track scale. So at track scale, we have approaches that will first distinguish particles. That's why I speak about particle approaches. And with two steps, I would say. One step, I will not insist that on that, but it is the objective is to simulate the spreading of the powder bed. That is done either with a roller or with a blade, and you can see here a lot of powder particles that will be spread to make a powder bed that will be exposed to the laser radiation. So that's a problem that is classically addressed with the discrete element method. I give you some references in this field. And what is also in the literature is numerical simulation in which each particle is discretized. It can be using ALE method, arbitrary Lagrangian Eulerian, or volume of fluid or level set methods. The aim being to really to assess the role of the size distribution of particles in order to see whether it impacts porosity effects or lack of fusion effects, for instance. But we should realize that such approaches are very time consuming. And I have indicated an order of magnitude. It's weeks per millimeter of scans that are necessary to make such a calculation. So in the literature, there are more frequently the approaches concentrate on an homogenized powder bed, not distinguishing between particles, but assigning homogenized properties to a powder bed that is considered as a continuum. And once you consider this, then you can think about different methods, ALE or interface capturing with level set or volume of fluids. And I have summarized the main, let's say, features and advantages and drawbacks of the different methods. So I will not comment that in full detail. On the right columns, I have given you some references that are significant in this domain. The ALE, okay, the advantage of the ALE is that only the metal domain is meshed, so which is good. But of course, metal-metal interaction is difficult to handle. The contact matter. So to treat instabilities of keyhole, for instance, is not very appropriate. What is nice is that surface forces can be directly integrated because you can integrate on the surface of the mesh, which is the surface of the material. And this is not the case for VOF or level set formulations. And in this case, the surface forces, they must be transformed as volume forces in the neighborhood of the interface in order to be taken into account. And the advantage is that metal-metal interaction can be simulated, and that even if only a few teams address this problem, the gas dynamics can be simulated as well, thanks to an effective two-fluid approach. So choosing between ALE and level set or VOF is not straightforward, I would say. It depends a lot on which software you use. Is it a commercial software proposing a solution or not? And it depends also on the precise objective of the simulations. Do you really want to simulate aerodynamics as well as the fluid flow or not? Okay. Well, I give you an overview on this slide of what is an approach by level set. So level set, you have the level set, what it means, you have a reference function, which is assigned the distance to the interface. So the interface is psi equals 0. And by this function, you can distinguish within a single mesh what is the gas domain and what is the metal domain. What is to say? Yeah, the level set, it allows you to realize a mix of properties within the transition zone that you can have around the zero level set. So this 2 epsilon thickness zone in which you will have to concentrate the mesh, to refine the mesh in order to express this mixing rule. So the mixing rule can be made in different ways. I don't insist that on that. And then you can transform the conservation equations that you will have to treat, conservation of energy, conservation of momentum, and conservation of mass, by doing this mix of properties. And the transformation of the surface forces into volume forces is made by this Dirac function. And Dirac function is the derivation of the Heaviside function. So Heaviside function will vary from 0 in one domain, for instance, gas, to metal domain, sorry. And the Dirac function, the spatial derivative of h with respect to the distance function, it will allow us to transform surface forces in volume forces. Okay. So the ingredients of a thermofluid track scale simulation is, sorry, I have, yeah, okay, is a module for laser interaction, capable of treating different beam types, considering surface absorption, or I've indicated Berlambert, but Berlambert is used for the impact of the beam on the powder bed. But I've not mentioned this, but we have to realize that during laser scanning, the beam interacts essentially with the melt pool, with the liquid, not with the powder bed. So it's a continuous advancing melt pool in the powder bed, but the laser is on the liquid melt pool. So we have to consider essentially surface absorption. And this might be done by ray tracing. I will say a few words of that in a few slides. So we need a heat transfer solver to treat nonlinearities, fusion, solidification, of course, and also considering what is important, the conductivity of the powder bed, which is very decreased with respect to the conductivity of metal, of course, because of the presence of 50% of gas within the powder bed. We need a flow solver with level set control of the interface, and we need an adaptive remesher in order to concentrate the mesh where it's necessary, and distinguishing, for instance, the powder bed from the substrate, from the deposit. Okay, so at each time increment, we chain heat transfer, fluid flow, transport of level set, and adaptive remeshing. Okay, an example of that, single track of Inconel 738. Experiments were done at Centre des Matériaux Mines Paris by David Grange, and the simulation was done by Alexis Keva in CNF. And you can see here on this process window, I would say, power of the laser vertically, velocity of the laser horizontally. This is in green, this is the window that is considered okay for additive manufacturing. When you go on the top left, you enter the keyhole regime with risk of entrapment of porosity. And when you are in this regime, low power, high velocity, you are in danger because of a lack of fusion or discontinuities of the tracks, what we call bowling. And you can see that on several couples power velocity, the agreement between the experiment and numerics is very nice. Okay. So this is shown a little bit more in detail on this slide, where we have longitudinal sections and transverse sections. And of course, the more you increase the density of energy, so this is the power of the laser divided by the velocity, that gives you joule per millimeter. And that's a good indicator of the intensity of the energy input. And when you increase this, you a more deep keyhole, like you can see here. So just to realize that we have to adapt the equivalent absorption coefficient if we consider only a Gaussian beam plus an influence of the incident angle. In this case, we have to increase the absorption coefficient with the linear energy. And that's explained by the fact that the beam will be, in fact, in reality, reflected successively once a keyhole is formed. And that's why, starting from A nominally, I told you that in one of the first slides, A is about 0.3, but in fact, because of the successive multiple reflections, it can be as high as 0.8. So to avoid the requirement of this artificial increase of A, ray tracing is a good method. So you discretize the beam in a great quantity of elementary rays, which are carrier of a certain energy or a certain power, more precisely. And then geometrically, you analyze the trajectory of each elementary ray and its reflection. So, which is not so obvious if you have a level set formulation in which the surface is not really obvious. So I don't insist that much, but there are a lot of geometrical calculation in order to identify the element target that is hit by each of elementary beams and the reflection, the power that is reflected is 1 minus A, the power that of the incident ray. Okay, so just an illustration. Without ray tracing, if A is 0.45, you have these results. This is a top view. This is a longitudinal view. You can see that, yes, the surface is deflected. But once you take into account multiple reflections thanks to ray tracing, in fact, you can see that the deflection is more marked and the apparent absorption coefficient is as high as 0.63, so which is a 50% increase with respect to the 0.45 initial. So that's very important to control, to implement ray tracing, I think, to be more predictive in terms of energy. Regarding validation, infrared imaging is really a wonderful tool once calibrated. So a lot of issues behind this, but I don't insist. And we made a very nice comparison in the PhD of Alexei Keva with respect to infrared experiment imaging from NIST, North America. So here you can see that's the longitudinal scanning direction, X, and this is where the laser is at the front, and this is the melt pool, this is the solidification transition, so the mushy zone, and this is the bead, the track during solidification with a very nice agreement that we have all along this cooling. So very, very good validation. Well, so once elementary track is mastered, is control, you can think about going to multiple tracks, like in this animation from Alexei Keva. We can imagine it's a lattice pillar, and we can see successive spreading of powder bed and then another series of laser scanning. And if you observe, then because of the accumulation of heat, the melt pool is enlarged from one layer to the next. Okay, so I would like to go to the next slide. So now solid mechanics at track scale. This is still to be explored. So we have seen what can be done regarding calculation of the shape of the melt pool, of the flows within the melt pool. And now, if we would like to combine with stress, because we want to predict fracture, so we need thermomechanics in the solid. So there are only very few teams that provide results combining fluid flow and stress. So I have listed a few of them. The more significant result that we have, I think, is the one from Singapore University, combining the growth of the grains with solid state mechanics. Well, this is difficult. This is difficult to combine liquid and solid mechanics, and this gives rise to, I think, a lack of continuity, consistency between CFD study and solid mechanics analysis, and very complex workflows in general. Since people, they play with Flow 3D, then Abacus with a lot of mapping. And well, when we addressed this problem, we decided to stay in the same formulation, proceeding still with level set, and only adding resolution for solid mechanics in our resolution schema. Like proposed here, only the solid mechanic bricks is implemented. So we have solid mechanics, but we have still at the same time liquid to treat in a second resolution. And for this, we proceeded like we did in casting, actually. We make a transition between behavior in the solid, let's say below the solidus, which is elastic viscoplastic, and up to the liquidus, which is Newtonian. And this transition can be formalized by a transition function that will be function of the liquid fraction. And in the PhD of Zixuan Li, that has been recently defended, that's what we have done with such a mix between a stress that is computed by an elastic viscoplastic law and a stress that is computed by a Newtonian law. And then, because we are at small scale, we are in presence of only a few grains, let's say not many grains like in casting of big parts. Here we can distinguish the growth of grains, and that's why in this PhD of Zixuan Li, we decided to inform the mechanics by the growth of the crystals, the growth of grains. So this is done by a very popular method that has been developed years ago by Charles-André Gandin and Michel Rapin, and which is based on cellular automata, so you have another grid, in addition to the finite element grid, you have another grid that is much finer, and that is able to capture the growth of the envelope of grains. So not really the dendritic growth of each dendritic arm, but the envelope of grains that are captured by this method. So I don't insist because it has been fully documented. And with respect to the link with solid mechanics, the mesh can be fine. So we can choose a very simple option, which is in one element, we will consider only a single crystal orientation. So we have grains that are predicted on the cellular automata grid, and we have finite elements here in red, and at the center of each finite element, we will take the orientations of the grain as predicted by the CA. And this is, of course, under the form of a set of 3 Euler angles. And each element is, in fact, colored by this crystal orientation. So a very simple scheme. And based on that, the mechanics is calculated using crystal plasticity. So here it's crystal viscoplasticity because we need viscoplasticity because we are at high temperature. So we use the cubic symmetry that is characteristic of alloys of interest like nickel or austenitic stainless steel. We have a finite a discrete number of sleep systems, and aligning the reference frame with 100 directions, we are able to express the decomposition of the strain rate into an elastic part with an anisotropic elastic matrix, a viscoplastic part, and the viscoplastic part is defined based on the shear rate within each sleep systems, plus the Schmidt tensor, and the Schmidt tensor that depends on the normal to the sleep system and the direction of sleep. And for that, we have different constitutive equations, power law, as you can see here, or also power law, not detailed in this slide, but based on the dislocation density for each sleep systems. So I don't insist that much. We can solve within each finite element. We have a nonlinear equation that we can be cast either in strain with the unknowns strain rate, but we have chosen to select the deviator as an unknown. So we have 5 unknowns. And we are able to calculate the stress deviator and the tangent modulus in order to transfer this information to solve the global equilibrium. So we are able to make this concurrent solution between fluid dynamics and solid mechanics at each time increment. And that's what has been done by Zixuan Li. So here we have an example of the scanning of an elementary track. And what you will see here is the formation of the epitaxial growth as the melt pool is advancing within the substrate and within the powder bed. So the powder bed is not seen in this representation. And here you will see the formation of the stress distribution. So that's the grain growth.
Okay,
and
you
that's
interrupt. You have more or less 10 minutes, please.
Okay, fine.
Thank you.
Yeah. Okay, so just a few slides. I will not comment this slide, but you can see that once you have the possibility of calculating a single track, then you can repeat several tracks side to side. And the last 10 minutes, I will insist on the numerical simulation at part scale. So at part scale, obviously, the detail of the laser trajectories cannot be replicated. And we must process by what I call a batch approach, grouping scan lines in layers, for instance, or even in full layers, or even in meta layers or super layers that will be deposited successively to create the part. And generally in the literature, that is done within 2 different contexts, either a quiet element in which the part is, let's say the potential part is fully meshed, and then you activate according to the rules, you activate layer by layer or fraction of layer by fraction of layer, you activate your elements. Or element birth, you create elements successively. There is one constraint with this method is that the mesh must be structured, which is a strong constraint preventing an efficient adaptive remeshing. So what we preferred, and this has been developed by Yancheng Zheng, essentially at CMF, is to do this addition of layers of or layer fraction within a level set formulation. So the level set will signify the growth of the part, and that's an advantage also, since we can make the thermal computation within a single mesh, also involving the non-scan powder, which has a significant impact because of this low thermal diffusivity. Okay, so that's what we call in the literature the flash heating method, since you bring the material and you must bring at the same time energy. And that's rather critical, how to bring this energy. If you consider a layer of fraction of a certain surface, then you know the scan time that will be needed to scan this surface. If h is the hatch distance and v is the laser scanning velocity, then the S is equal to hv times t-scan. So you know the t-scan, and the heating time, the time during which you will heat this yellow domain, is in fact the interaction time that the matter has with the laser. And this interaction time, it is the phi, the diameter of the laser beam, divided by the velocity. And you introduce a coefficient alpha because in fact this phi divided by v is very short. So alpha is a mitigator, making the problem less stiff, I would say. And what you write, once you know T-scan, once you have evaluated T-heat, you write a balance of energy. You have a laser of power L working during, being on, let's say, during a time T-scan with an absorption factor A. And on the right-hand side, this allows you to define a volumetric volume input power in the volume during the heating time that you have decided. So that's the flash heating method. And what you need to perform thermomechanics, so I will be brief, you need a slicer, everybody knows that. You have a module to determine the layer fractions. For instance, this is the criterion, it is on the scanned distance that will define what is a layer fraction. Then you have you need a mesh and a level set formulation. You need a thermal solver, of course. You need an adaptive remesher, that's best. A mechanical solver with the same principle I told you for the track scale. And here, to solve mechanics, then what we did with Yancheng Zheng is that we distinguish two meshes, in fact, because the loose powder that is non-scanned has a zero role regarding mechanics, so we can suppress it in order to save computation time, calculating the mechanics only on this part. Okay. An example of an instrumentation that was very nice to validate such formulation. It is forming a deposition on a thin substrate equipped with mechanical sensors. And the advantage is that because of the cycle of the heating and cooling, the substrate reacts by bending, and we can follow this with mechanical sensors. So this was calculated, and on that you have the comparison of heat transfer, so heating with the different cycles, and more interesting, the displacement of the substrate and how it is captured by the thermomechanical simulation. So you can see that, yes, we can compare successfully with the experiment. Uh, so we applied this at the scale of more complex parts. And here I give you an animation of the temperature. So this is what, on the left, this is what we can see through the window of an additive manufacturing machine, in fact, and the laser is at work on the powder bed, and it selectively you have the melting of the material. And here, the powder bed, the non-scan powder has been removed, and we can see only the build-up of stress within the part. So I will not insist that much on macro scale calculation, and there is a lot of literature on quantitative validation of flash heating method in thermomechanics. And I recommend the two articles of Sciumenti and Santi and Attel from Danish Technical University. Okay, and what we are doing at CEMEF is also to think about informing thermomechanics at part scale by grain structure. So this is a challenge because it's not easy to generate grain structure at part scale. It's more easy to do that by CA at track scale, but at part scale it's more difficult. And here is an approach that has been suggested by, proposed by Camus, Gilles Daguillemot, and Charles-André Gandin. It comes from thermohydraulics, that is, so track scale simulation that is performed up to the steady state. And then you map the result in terms of temperature onto the part scale according to the scan path, so respecting the exact scan path, and through the cellular automata, you can generate the grain structure either at a representative volume element or even at part scale, provided the part is not too big, I would say. And once you have done this, using this hybrid approach, so you generate the grain structure along the part, and in a second step, you activate the heat transfer calculation at the scale of the part using the level set formulation, and the mechanics as well. So to perform the mechanics, you must consider the input of the grain structure and the input of the temperature provided by the heat transfer analysis. And that allows us to calculate the progressive buildup of stress during a part construction. So a demonstration was done on this turbine propeller in Connell 718. So this is the microstructure, the grain structure as calculated by the cellular automata. This is the mesh for the heat transfer, and this is the second mesh that is considered only for mechanics. So this is for a small part, very small part. In fact, it's a kind of demonstration. For the moment, we would not be able to do that on, let's say, real scale parts. But so maybe it's not necessary that I comment fully in detail, but it's just to show you that yes, we are on the way to couple grain structure formation and thermomechanics, essentially at track scale for sure, but also at part scale. So I will maybe not comment fully this and insist more on the conclusion, since I understand that the time is I should conclude. So the conclusions, and maybe that's some points that we can discuss together in the final session. So I think we agree that in the community, track and part scale thermomechanical simulation are really intensively developed. At part scale, the state of the art remains the flash heating method, which is not fully satisfying. Not fully satisfying because, in fact, it cannot reflect the influence of the scan path on the residual stress. Besides, there are some questions regarding how anisotropy can be addressed, because we know that we are creating oriented grains, oriented microstructures, so for sure an isotropic response of the material. And but this is really an issue if we don't inform mechanics by grain structure formation, like I just showed you, how to account for anisotropy in, let's say, standard behavior laws. That's really an issue. So to go ahead, there are two main challenges. How to generate grain structure in reasonable times for parts of a few tens of centimeters, which is not solved at that moment. And more than this, how to control computation time to solve thermomechanics while considering the effective, the real laser scan path, which is a huge challenge at the present time. At track scale, then I think that coupling cellular automata and crystal plasticity, it opens a very promising avenue because anisotropy, it is informed by the growth of the grains. So provided that you are able to characterize the behavior of your material under the shape of single crystals, and that's possible, that's definitely possible to do that, to do this, then you can really perform track scale relevant thermomechanics. So this needs obviously quantitative validation, and measurement of dislocation densities, measurement of stress at grain scale is really a challenge. Yes, this is ready to be used for hot cracking prediction. So we need validation, but after that, we are ready to predict hot cracking and realizing that hot cracking granular cracking. So it's very nice to have the grain structure predicted in this context. And the final remark is that the link between part scale and track scale is definitely still underexploited. For instance, there are very few track scale simulations in the literature that are performed considering the texture of the previously deposited material, the temperature distribution of the previously deposited material. So this is totally underexploited for better predicting thermomechanical features and defects. So that's my final word, and I thank you all for your attention.
Thank you very much for your insightful presentations. And now we just move to the second part, questions and comments. We already have some questions on the chat. I don't know if the people who write want to talk. Olivier. Okay, this is the first question. He asked, do you use the fast field approach to track the interface?
Excuse me, it's in the chat? That's what I understand?
So the first question was, do you use the fast field approach to track the interface?
No, definitely we didn't use the phase field approach. So in the literature, the phase field approach is mostly used really to track the interface at a smaller scale, I would say, that at the scale of the dendritic arms, less frequently to predict the growth of grains. And in fact, I think it's a little bit early, a little bit too early to consider the scale of dendritic arms. And why I say this, I also say this because we are a little bit obsessed by solidification cracking, I would say. And in this respect, as I told in my conclusion, solidification cracking is an intergranular cracking. So I think the right scale is the grain scale for the moment. Maybe in 10 years from now, the dendritic scale will be the more relevant one, but it's still too costly.
Thank you. Maybe I will pass the word to Muhammad Ali because he raised the hand.
Can you hear me?
Yeah,
Yes.
definitely.
First of all, thank you, Professor Bellet, for the wonderful presentation. My question is that over the last few years, say 1 decade or so, additive manufacturing could not enter into the industry as it was expected, like a game changer in manufacturing. So maybe in my opinion, one aspect is standardization, that the complexity of processes have not been standardized. So in your wise opinion, what are the measures that we should take so that it can enter into the industry? Thank you.
Okay, so thanks for the question. I would simply say that I am definitely not the relevant person to answer to such a question. Uh, as you have seen, I am very much focused on the scientist point of view. I am a scientist developing new methods and really, I think my point of view wouldn't be so relevant regarding why additive manufacturing has not the expected success in industry, well, because there are too many factors that are at stake. Really, I don't want to enter to this debate. Sorry for that.
Okay,
Maybe
thank you.
my answer is disappointing, but
Okay, maybe we just move. Thank you. Move for the next questions. Adinal Gavrus, please.
Hello, everybody. Hello, Michel. Adinal Gavrus in Sarena, Betania. Just, I have a question about possibility to use optimization to minimize residual stresses. And if compared the residual stresses of simulation with experimental ones, first question. And second one, if effectively possible to make an optimization of trajectory of other variable of the laser welding of manufacturing laser to minimize residual stresses.
yes. Okay. Thank you, Adinel, and I say a special hello to you, as we have worked together actually years ago. Okay, optimization. Yeah, optimization. So just consider that, let's say, direct simulations, direct calculations are already very time consuming. So at the moment, thinking about optimization can be only the only way would be deep learning. So training, constituting a training base and looking for optimization. But optimization based on direct simulation, as I have just shown you, is not feasible. So I have not implemented this in my conclusion slide, but definitely deep learning, artificial intelligence is the next step also. Yeah. Especially, I think, and that's in the literature, we can see some contributions appearing regarding fluid flow and prediction of temperature field based on deep learning analysis. Not yet for mechanics, but that's the next step for sure.
Yeah. I
So,
think that I don't know if exists actually for laser welding, for example, because the complexity of the numerical simulation is very high. But minimal to have a comparison between experimental residual stresses from the PACs and simulated ones is the first step. After optimization, it's second steps have values of power of the laser, of orientation of the laser, or trajectory. You try to obtain a minimum residual stresses in the pieces.
yeah, the one of the best comparison of residual stress I have seen is very recent. It is due to the team in DTU by Jesper Hattel and Alberto Santi. He will defend his PhD next week, and I will be in his committee. And he has made a very nice comparison of at part scale. Comparison with neutron diffraction and X-ray analysis. Excellent work. So it is in my in the PDF. I think I will send all of you the PDF of my conference, but the reference is in there.
Thank you.
Thank you very much.
We have several questions. Maybe I will give the word to the people who raise the hand and to the others that are put on the chat. Maybe you can just reply by email, because I don't know if we have time to.
Yep. Okay.
So Frank Scharfert, please.
Yeah, thank you very much for the presentation. Actually, it fits very well. My question fits very well to what Adinel just mentioned, the use of artificial intelligence. I'm wondering, do you have experience in speeding up, especially the melt pool simulation, for example, by using what people are now developing in the context of neural operator networks? For example, the CFD simulations by ETH in Zurich, or the Tsinghua University with their model Neuron. Do you have experience? Are you planning something? How would you consider this approach? How successful?
Yeah, as I said, that's the next step. Definitely, yeah. We are considering this, obviously, yeah. But we are not. I was not able to show significant results for the moment. But yes,
so you are already working on that.
Yeah,
and
we will work on that.
And what specifically are you modeling? Are you modeling the CFD part? Are you modeling the ray tracing part? Are you modeling the thermal part, or all together?
Well, what we would like to do first is to accelerate, let's say, the metallurgy, the coupling between metallurgy and thermomechanics. So that's the domain in which we need artificial intelligence. It is to implement, let's say, metallurgical modules that should be compatible with the thermomechanics calculations.
Okay, thank you.
So the last questions from Siddharth Pradep, please.
Yeah, hello. Thank you for the presentation. And my question is regarding the part scale, not part scales, track scale, where you told you have combined the cellular automate with crystal plasticity. Is it two-way coupled? So that is my first question. The second question would be, wouldn't we get a better if we have a coupling between fluid and solid equations? Like if fluid with Darcy with solid mechanic models together. Like, so isn't that a good way, or maybe solve it in same variables like pressure, velocity for both solid and fluid? So yeah, that's my
Okay,
question.
so I try to answer the first question first. Coupling cellular automata and crystal plasticity, it is a single, a one-way couple. It is a stagger scheme, I would say. With the CA, you predict the grain structure, and you map this grain structure, you give the information to the elements in charge of calculating mechanics. That's very simply. There is no feedback from mechanics to grain growth anyway.
Okay.
It's okay for you?
Yeah, it's good.
So now,
yeah.
the second part of the question, I understand it is on how do we couple fluid flow and thermomechanics, basically. So you talk about Darcy terms. So at that moment, within the fluid flow solver, we don't have Darcy. Let's say when we perform the fluid flow resolution, we make the dynamic viscosity vary between an arbitrary value in the solid and the nominal value in the liquid.
Okay.
But that's a classical way to treat liquid flow in such melt pools. But I agree with you that it would be definitely better if we consider the Darcy terms. That's what we did very classically when simulating casting processes. So it's not done in our additive manufacturing application, but it would be easy, I would say. It would be better to consider Darcy for sure.
Yeah. Thank you.
Okay, thank you. Okay, so the last questions, because Victor Facchinotti is there. I will let one more questions and then we have to finish.
Okay, can you hear me?
Yes, Victor.
Thank you very much, Michel, for such a complete presentation. But yeah, looking at your very, very accurate prediction of the whirlpool with the track model, I was thinking of using this result to train a neural network to define a more accurate heat surf model at the macro scale. Have you tried it?
No, I'm not sure I have well understood you, Victor. So is it because
Yeah,
because
to define a better Goldax, a better alternative to Goldax heat source. With
yes.
maybe you can not have a close analytical form like Goldax, but you can train an artificial neural network depending on all the parameters that you think that have an influence on the shape.
Yes.
And to use this more accurate model at the macroscopic scale.
So I think I understand your point. And there is one magic word I have not pronounced in the presentation is Goldax.
Yeah.
So just maybe a few words about Goldak's approach, which is very popular, in fact. And in fact, well, why do people use Goldak? It's because it allows you to reach approximately the same results, but without solving really fluid flow. So there are many teams that try to train Goldak or to determine Goldak parameters based on upstream fluid flow calculation. So that's one approach. So very high fidelity fluid flow calculation. Then you, based on that, you try to identify the parameters of the Goldak source. And based on that, you realize faster track scale simulation, allowing the determination of the temperature profile, and so possibly thermomechanics downstream. That's an approach. I don't like it very much, but that's an approach. For me, Goldak should be avoided anyway. We should go directly, and that's what I illustrated in my talk. I consider it will be always better to go directly from high fidelity fluid flow calculations to mechanics, to solid mechanics.
But I was thinking of a way of avoiding this very, very expensive calculation at the track scale.
That's one way, which is it's popular in the community. This intermediate step, which is a Goldak one, is quite popular.
No, I mean an alternative. Maybe distributing the heat in a double ellipsoid, you will not get the correct shape of a melt pool. But if
you will not get the shape will not be as good as when using high fidelity for sure.
Yeah, but
you could think about refining.
I'm sorry, we have to interrupt this high-level discussion of specialists of solidification. We are overpassed the time for the webinar, and this discussion means that